Hello guys, so this video is a continuation of the previous one wherein we try to optimize our portfolio by maximizing its Sharpe ratio. In this video, we will be trying to evaluate our portfolio's risk and return using the Monte Carlo method. Now, essentially what we're going to do here is that we're going to simulate a lot of different scenarios, a lot of different portfolios like around 1000 to 10,000 and try to calculate its expected return based on this fact or based on this assumption that stock prices follow this thing called GBM or geometric Brownian motion. Now this is the whole idea of this video, right? So we try to simulate a lot of different portfolios and calculate its expected return based on or using the weights of the portfolio that we calculated in the previous video and the forecasted returns of each stock that we calculate using GBM. So let's begin. Before we begin, I should also mention that I've put the link of this Jupyter notebook in the description, so feel free to check it out. Let's start with what GBM is, or geometric Brownian motion. So as I mentioned before, the movement of stock prices can be modeled using this GBM. It's simply just a stochastic process and the stochastic differential equation is given by this right over here. dSt is equals to mu times st times dt plus sigma st times dbt. Here st is obviously your assets price, mu is the mean, sigma is your variance and bt is just Brownian motion. And this SDE has two terms. The first one is a deterministic growth or the drift, while the second one is a random shock or scaled Brownian noise. So our aim now is to solve this SDE, right, to get an expression for ST. But there's a problem. The problem is that the Brownian motion as seen in assets prices is continuous everywhere, but it is differentiable nowhere, because of which this SDE becomes impossible to solve by calculus's conventional means. And so there's this guy Kiyoshi Ito, he developed a technique using the Taylor series expansion to solve this SDE. So let's see what he has done. So we have a stochastic differential equation here, which is dSt is equals to mu times st dt plus sigma st dbt, right? So now let's define a function f of st, where f of st is basically equal to log of st, right? Now I will use the Taylor series expansion to write df. So df will be equals to f dash st or f dash dst, right, plus half of f double dash dst whole square, and I'll be neglecting the the higher derivatives. So now we know what f dash is. F dash is simply the derivative of log st, which is 1 over st, and f double dash is simply the derivative of 1 by st, which is minus of 1 by st square, and dst is what we have here, right, the original expression, and dst whole square can easily be found out by just squaring the first expression. So d of st square is simply the square of this first expression here. Well, this expression is the form of a plus b, right? So dst square is simply a square plus b square plus 2ab. So your a square is going to be mu square st square dt square. Your b square is going to be sigma square st square dbt square, and your 2ab term is simply going to be 2 mu sigma st square dt dbt, right? There's one thing to note here, that since dt tends to 0, your dt square and dt times dbt will also tend to 0. But what about dbt square? Well, there's something called the quadratic variation of a Wiener process, which states that bt square is basically O of t, and so dbt square will basically be O of dt. And hence, the first term here will be 0, the last term here will be 0, and this middle term will be sigma square st square dt. And so, one can just quickly plug in all these values that we have gotten here into df to get that f dash dst is simply 1 over st, dst is mu st dt plus sigma st dbt, right? And then the second term, which is minus half 1 over st square times sigma square st square dt, right? So let's cancel out st from the first term and st square from the second term. Let's also rearrange this entire expression to first collect terms which have dt, right? So mu minus sigma square upon 2, and then let's write the last term, which is sigma dbt. Alright, so this is our SDE, which we can easily solve to get log st, because our f is like f of st is just log of st, right? So when you solve this expression, you get log of st is equals to log of s naught plus mu minus sigma square upon 2 times t plus sigma bt, right? And so one could easily exponentiate this to get the clear expression for st. So st is equals to s naught e to the power mu minus sigma square upon 2 times t plus sigma bt, right? And so this is the expression that you get for st. I also forgot to mention that I have written the derivation of Ito's lemma here, so those who are interested can feel free to check this in my notebook. Alright, so we have gotten our expression for st, which is st is equals to s naught e to the power sigma bt plus mu minus sigma square upon 2 times t. But this is just for a single asset. This expression for GBM, which is the geometric Brownian motion, is for a single asset. How about when we have n stocks, when we have n assets? Let's move over to M-GBM, where M stands for multidimensional, and let's analyze what happens. Now, in our GBM for single asset, we just had a single scalar st, right? But now since we have n assets, we'll have a price vector st which has n terms in it, si comma t, and it is associated with its mean vector mu, whose terms are mu1 till mu n. Now, if one just simply and naively extends GBM to this, n stocks M-GBM, then component wise you get d si comma t is equals to mu I times si comma t times dt plus sigma I si comma t times dbi comma t. And one can easily write this in the vector notation, vector format. But this is a problem, right? This assumes that all Brownian motions bi comma t are independent and that the volatility is just a list of scalars. But this is not what happens in reality. In reality, all the stocks are correlated, and if a certain stock A shocks up, then so does stock B, because their randomness is correlated. And so instead of just defining one Brownian per asset, where in the GBM example we had BT, we will define a vector W. This vector W contains independent Brownian motions. So as you can see, WT will be a vector whose terms are going to be in the form of Wi comma t. And so we'll mix all of these so that the stocks become correlated. Let's go back to the drift term that we had in a single asset case. So there, the drift term was simply mu times st times dt, right? How is it going to change in this example of n stocks? Well, now I'll define st to be a matrix whose diagonal consists of the prices of our different stocks, right? So as you can see here, this is going to be our diagonal matrix, our diagonal st, right? And this mu will just be our mean vector for different stocks. So now the matrix multiplication of this will simply give us mu I times si comma t, right? Similarly, the volatility also becomes a matrix. Instead of having just a single scalar or a vector sigma I, we'll use a matrix gamma. So this gamma has its elements gamma I comma j. Now what does this gamma tell you? Well, see, we have our W vector with us, which basically consists of independent Brownian motions with us, right? Now every row of this gamma tells us how each Brownian motion in this vector W contributes to stock I. So you have this row, right? Let's say you're talking about stock I. So its corresponding row in this gamma vector tells me how much how much each Brownian motion in this W vector contributes to stock I, because this row gets multiplied by this column vector W in matrix multiplication, right? So this essentially, this random part becomes diagonal of st, diagonal matrix times gamma times dwt. And so if one wants to write it component wise, seeing for every asset, then the expression is simply mu I times si comma t times dt plus si comma t, the summation from k is goes to 1 till n gamma ik times dw kt. Now this summation is pretty obvious, right? This summation comes from the matrix multiplication of gamma and dwt. So before proceeding to solve this SDE for the M-GBM case, there's something that one should note. Well, it turns out that the matrix multiplication of gamma with its transpose gives us a covariance matrix. And if someone has a target kind of covariance matrix in his mind, that he wants this to be his covariance matrix, then he can find out what his gamma should be. This technique of finding what the gamma should be given a certain target covariance matrix can be done by something called the Cholesky decomposition. We will not be coding for it, but we'll be calling this function from the linear algebra module in NumPy. So just to reiterate, Wt is a column vector whose elements are independent shocks, and our gamma Wt, which is the matrix multiplication of gamma and Wt, gives us the correlated shocks whose covariance is gamma gamma transpose. So now let's derive the solution for M-GBM. So our SDE for M-GBM was simply dst is equals to diagonal ST, the diagonal matrix, times mu vector times dt plus diagonal ST times gamma times dwt, right? So if someone wants to write this component wise, as we have seen earlier, is going to be something like dsi comma t is equals to mu I si comma t times dt plus si comma t, the summation from k is equals to 1 till n, where n is the number of assets, gamma. So let's say that the elements of the gamma matrix is gamma uh, I comma k dwk comma t, right? So now we'll be trying to solve this SDE right over here. Now, similar to the case for GBM for a single asset where we had defined the function f of st is equal to log of st, similarly we could define for each asset here in this M-GBM case the function f s I comma t is equals to log s I comma t, right? And so similarly one could write the expression for df using Taylor series expansion. So df would be, what would df be? Df would be f dash s dsi comma t plus half of f double dash dsi comma t square, right? Now f dash is simply 1 over si comma t, because f of si comma t is equal to log si comma t, right? And your f double dash will be minus 1 over si comma t square. Your dsi comma t is just this expression right over here, right? And this is what we are trying to figure out. So let's figure out what dsi comma t whole square would be. Well, our dsi comma t is, the expression for that is right here, right? So this contains two terms, a and b. A contains dt and b contains dwk comma t. So when we try to calculate a square, we see that we get a dt whole square in that, which tends to 0 since dt tends to 0, and so a square tends to 0. What about b square? Or before that, let's figure out what 2ab will be. Well, 2ab will contain terms that contain dt times dwk comma t, which would tend to 0 since dt tends to 0 again. So 2ab will also tend to 0. How about b square? Well, there's something to note in this. dwk comma t times dwj comma t, where k is not j, will tend to 0, while dwk comma t whole square will basically follow from what we had done in our GBM case as well. So as we had noted before, that dwk comma t, or actually wk comma t whole square, is basically O of t, and so dwk comma t whole square is basically O of dt. So that you can transform your dwk comma t whole square to dt. So our dsi comma t whole square is simply then going to be si comma t whole square, the summation from k is equals to 1 till n gamma I comma k square dt, right? And so one could now easily write the expression for df, which is going to be 1 over si comma t. dsi comma t is what we have over here, which is mu I si comma t dt plus si comma t summation k is equals to 1 till n gamma I comma k dwk comma t plus this second term here, which is half of minus 1 over si comma t square times si comma t square, the summation from k is equals to 1 till n gamma I comma k square times dt. Alright, so now let's cancel out some terms, sit square, and let's now group the terms which have dt. So mu I dt plus the second term here, which is the minus of the summation gamma I comma k square dt, summation from k is equals to 1 till n whole divided by 2, right? Plus there's another term that we're forgetting, which is the summation from k is equals to 1 till n gamma I comma k dwk comma t, right? Now in order to proceed and to help compress this complex expression here, we need to observe one thing. Observe that the diagonal vector of the matrix multiplication of gamma with its transpose gives me a column vector of this form, summation gamma I comma k square, where k is from 1 till n. How? Well, one could just explain this by just multiplying gamma and its transpose. So Gamma times gamma transpose is just us multiplying the matrix gamma with its transpose here, right? And observe one thing, that the ith row of gamma will just be the ith column of your gamma transpose. And when we talk about the diagonal elements of gamma gamma transpose, then the diagonal elements will be of the form of I comma I, right? So consider the I comma ith element of gamma gamma transpose. That would just mean us multiplying the ith row of gamma with the ith column of gamma transpose. Basically we're multiplying two identical vectors, right? And you would simply just get the summation of gamma I comma k whole square. So we could just replace this term right over here, the summation of gamma I k square, where k is from 1 till n, with this term right over here. This helps us compress everything, because then you could write your df something like this. So one can now write conveniently what the df would be. Well, df, or actually d log st, right? So d log st will simply be is equals to mu minus half of the diagonal vector of this matrix multiplication of gamma with its transpose, right, times dt, plus this second term here. This term is simply just the matrix multiplication of gamma with dwt, right? So gamma times dwk, or dwt, my bad. And one can easily solve this to get log st is equals to log s naught plus mu minus half diagonal of gamma gamma transpose times t plus gamma dw, not d, it's just going to be wt, right? And so one could just simply exponentiate this to get st is equals to s naught times e to the power mu minus half diagonal of this matrix, right, times t plus gamma wt. And so we get what our expression for st would be. It would be st is equals to s naught times e to the power mu minus half diagonal gamma gamma transpose times t plus gamma wt. So now that we have finally gotten what our expression for st should be, let's finally rewrite the code for defining the Monte Carlo simulation and calculating our results. So let's go and first make a new notebook. Let's call it YT portfolio eval, right? So let's first import the numpy package, right? Import numpy as np, and let's begin to write the code for the Monte Carlo function. This takes in inputs weights, the returns, the initial investment that we want to give, the number of years, the number of trading years, and the number of simulations that you want your Monte Carlo to have, right? Then we can proceed by just simply figuring out what the number of days would be. It would simply be number of years times 252. We'll multiply by 252 because we usually consider there to be 252 trading days in an year. And we'll also figure out what the number of assets would be. The number of assets would simply be the columns in our returns matrix. So returns, or the length of returns dot columns, right? And then we can try to get our mean vector from our returns. So mu returns would be returns dot mean, and we can also similarly figure out what our covariance matrix would be. This would simply be returns dot cov, right? And now remember one thing, we had discussed that gamma times its transpose, or the matrix multiplication of gamma with its transpose, would equal to the covariance matrix that we want. And since we have given our target covariance, we can use Cholesky decomposition to get what our gamma would be. So L, let's call gamma L. So L will be equals to numpy np dot lean algebra dot Cholesky, I hope that's the spelling, and then we are passing our parameter cov returns, right? And finally let's define our our final portfolio values vector, which contains the values for each simulation, the final values that each simulation gives us back. So the final portfolio vals would simply be numpy dot zeros, right, and the number of simulations that we are having with us. There we go. Now let's code for the loop. Let's figure out what do we write in our loop, right? So for I in range num simulations, right? So we have to basically calculate two terms, the drift term and this correlated noise term, right? So let's first calculate the second term. So it's we have to basically calculate L times W. So for getting our W matrix, we are going to sample the terms from a normal distribution. So W is equals to np dot random dot normal. Mean is 0, variance is 1. The number of rows would simply be the number of assets that we have, and the number of columns would simply be the number of trading days, which is num days, right? And then our correlated noise would simply be the matrix multiplication of L with W, right? Yeah. This now let's calculate our first term, which is the drift term. So our drift term is basically this expression here, mu minus half of the diagonal vector of gamma times gamma transpose. So our drift would be mu reds, right? Mu reds minus the diagonal vector of our covariance matrix, right? Because we know that gamma times gamma transpose is equals to our target covariance. So our covariance, right, upon 2, as simple as that. And since this will give me a row vector, I'll be transforming this into a column vector. So drift is equals to drift dot values dot reshape num assets comma 1, right? And finally I need to sum both of these terms, correlated noise and this drift term, and take its exponent. So our daily returns would simply be the sum of our drift, or actually it would be like, because see, daily returns, I'm defining daily returns to be st upon s naught, so that is equals to e to the power the sum of both the terms, right? So daily returns is equals to np dot exponent, and inside this we'll add up both our drift plus our correlated noise, right? And finally I will basically now I will, since we have gotten our daily returns, I will stack all of this row by row, in the sense each row will define the daily returns I get for that day, and finally I'll just take the cumulative product of it. So to get this stacked matrix, let's define our matrix to be price paths, right? This price paths is just a vertical stack of your, initially you have ones in your row, right? So np dot ones num assets, right? And I'm stacking this, I'm vertically stacking this with our daily returns. Now our daily returns has its columns to be different days, but in price paths I'm vertically stacking it according to the days, right? But the rows now represent my days, so I need to take the transpose of daily returns. So daily returns dot t, right? And finally I'll take the cumulative product of all of this. So come price paths would simply be the cumulative product of price paths, right? So price paths dot come product access equals to 0, since we're doing it row wise. Cool. Now let's figure out what our initial allocation is. So initial allocation would simply be initial investment times the weights, right? And we need to figure out how much our, the initial amount that we have given in every asset becomes after 1 year, right? So our final asset value will then become the, initial allocation times the last, value of the come price paths, the last row of this come price paths, right? So minus 1, right? And finally we need to put, the sum of all of this into our final portfolio values vector. So fin pf vals I would simply be the sum of final asset vals, right? And after all of this we'll just return our fin pf vals, and then let's use the code that tries to figure out the optimal portfolio weights that I've executed in the last video. So let's copy that code, which is this one, and get our optimal portfolio weights. Okay, so we have finally gotten our optimized weights in this optimized results x parameter, right? And now let's call in our Monte Carlo function that we have defined over here. So let's given our initial investment to be a lakh. So yeah, there we go. And then we also need to give in two more parameters, right? We have to give in the number of years. So let's give that to be 1. And finally, let's simulate this for 10,000 simulations. So num simuls is equals to 10,000, right? And let's call in this function Monte Carlo. And our final portfolio vals, or right, yeah, our final portfolio vals will be outputted. So let's call this function with all these parameters. So weights is actually optimized weights, right? So OPT weights, then our returns, which is what we've defined over here, right? Then our initial investment, which is a lakh, number of years, which is 1, and number of simulation, which is 10,000. So let's go and let's execute this, right? And finally, let's just display all our mean of all the final portfolio values, its standard deviation, the 5th percentile, the 95th percentile for analysis. Okay, seems like our simulations are finally complete, and now we can analyze the beautiful results that we get over here. So let me first explain you what I've done here. I'm calculating the mean of the final portfolio values because I'm trying to figure out what the expected portfolio value will be. And I'm also calculating the risk or the standard deviation of these final portfolio values to like kind of get a measure of the risk involved in this, and the 5th and the 95th percentile to figure out what the best case and the worst case would be. So let's see, we have gotten the expected portfolio value to be around 1.4 lakh, which is pretty good because it means that we have a 40% increment from our initial investment across an year, right? And this is accompanied with a standard deviation of 30,000. This means that there is a 68% chance that our final portfolio value will lie between 1.4 minus 30,000, which is 1.1 lakh, and 1.4 plus 30,000, which is 1.7 lakh. So there's a 68% chance that our final portfolio value will lie between 1.1 to 1.4 lakh, which is pretty good, pretty decent. Okay, so finally let me explain to you what VAR is. So VAR basically means value at risk, which basically kind of quantifies what the potential financial loss would be in an investment. So here, as we can see, that 5% of all simulations have resulted in the final value of going below 97%, which means that there's a 5% chance that we will lose about or lose at least 3% in this investment. So yeah, I think I've pretty much covered everything that I wanted to cover in this video. And if you guys felt that I kind of went a little fast in this video, then I apologize for that. And I would highly recommend you guys to check out this Jupyter notebook of mine, wherein I covered everything that I covered in this video in great detail. It also covers the derivation of Ito's lemma that we have not really used, but for those who are interested can definitely check it out. So thanks for watching guys, and definitely subscribe to my channel to stay tuned with the content that I upload. Bye bye.